of this was pre-made, so I kind of combined the two.
Should we turn the lights off?
Yeah, let's turn the lights off. You don't want to?
I want to.
Are you gonna be scared?
Yeah, I want to turn them on.
Hey.
Whoa! Why'd you do that?
You want to hear the Element song one more time?
Yeah.
But I think the camera does it.
Just so I can get it in my head.
One more time, we'll do the Element song.
Hey, if we sing this song
on the final.
If we memorize it, could we get extra bonus?
That's what I would punish, guy.
I'm not. Yeah, on the final. On the final, can we sing it?
Here.
I'm not memorizing crap.
Here's the periodic table.
Oh my! You could have done it on that track.
Oh, we got no volume. What?
There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, chromium, lithium, beryllium, and barium. There's holmium, and helium, and hafnium, and erbium, and phosphorus, and francium, and fluorine, and terbium, and manganese, and mercurium, molybdenum, and magnesium, dysprosium, and scandium, and cerium, and cesium, and lead, praseodymium, and platinum, plutonium, palladium, promethium, potassium, polonium, and tantalum, technetium, titanium, tellurium, and cadmium, and calcium, and chromium, and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, kryptonium, and radium, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard, and there may be many others, but they haven't been discovered.
One more time. One more time.
That, we should get extra credit.
One more.
I'm starting to memorize it.
One more time. One more.
I know some of it.
Yeah, I know.
I know the end was
At the very end, it goes real bad.
many others, but they haven't been discovered. That's all I know.
All right. We did this yesterday. So we're on 6.2. Which is on page 156. Are y'all on page 156?
Yes.
Get your book out and turn to page 156.
Can I look at my book? I have a book.
You don't have a book?
I have one. It's not locked.
Unbelievable. How many need a handout because their book hasn't come in? Didn't some of the people say that? Yes, you can go get your book.
Mine should be in Thursday.
Yeah, mine should be in today.
3. You need one? Well, go get it.
Why did you
Biology class without your biology stuff.
Where's your thing?
This is, from now on, this is biology class.
Where you should have your biology.
Bring your biology book.
What page is 150?
If I had a book, you guarantee it.
156. It says section 6.2. It's the first page of 6.2.
Where?
Now, these notes that are up here, you don't have to write them. Drew up here. You don't have to write these. All this stuff is in your book.
Oh, so you could like highlight in your book.
You could highlight. I go through sometimes I'll go through it real fast. Sometimes I'll go through it slow. You may have time to write it. You may not. So, however you want to do it. If you like to take notes, if that helps you, go ahead and do that. This actual presentation has a little button and stuff that you can click on to make noise. For instance,
Look at the button.
see the sound button? Watch this.
Chemical reaction. A chemical reaction is an energy-requiring process by which atoms or groups of atoms in substances are changed into different substances.
Why is it different than the words?
I don't know.
It's pretty cool, though.
That's our vocabulary.
Coolly. He talk, Meredith?
These two pictures are showing the differences between chemical reaction and physical reaction.
I don't think that worked.
Basically, In a chemical reaction, you have a fundamental change of the substance as its chemical formula is written. For instance, like if you take H2O and it goes through a chemical reaction, at the end of the reaction, it will no longer be H2O. The H's will be torn off, the O's will be torn off, and will be rearranged into some new compound. That's a chemical reaction. I'll show you some examples. Rusting is a chemical reaction. It's where the oxygen from the air combines with the metal from the cans and makes something new. That something new is called iron oxide. If you
Isn't that rust?
know much about rust.
I know everything there is
That's
to
what I
know
just
about
said. That's rust.
If I knew any more about rust, it would be scary.
Now, a physical reaction is when the compound, the formula of the compound doesn't change. So ice can melt into water, and that's y'all don't make stray comments, okay? If you make a stray comment about something, now people are listening to you and not to me. It could confuse them. So if you want to ask a question, you can raise your hand. That sort of thing. So when ice melts, it goes from solid to liquid. It's still H2O. It hasn't changed its chemical, its compound, its formula. So that's a physical reaction. So there are differences between a physical reaction and a chemical reaction. If I tear this paper, that's a physical reaction. I haven't chemically changed the paper. If I burn the paper, that's a chemical reaction. I've actually changed the formula. And it's hard for you to know what is a chemical and what is a physical reaction sometimes. Sometimes it's difficult to tell. Here's an example of a chemical reaction. This is the formula for glucose, C6H12O6. That's a formula you're going to have to know by heart. You can go ahead and memorize it now, or you can wait.
That whole
But anyway,
thing.
C6H12O6, that's glucose. That is a simple sugar, and that's very important in biology. Yes, question. Good, raise your hand.
Yes, I'm right now. Do I have to know the whole thing or just glucose?
You're going to have to know that for sure. Eventually, we'll have to know the whole formula. But C6H12O6 is glucose. You can go ahead and memorize it. That would probably help you.
Isn't that in food?
Glucose is a sugar, is a simple sugar.
Do you eat sugar food? So
That's what your cells,
Say sugar.
up here, that's what your cells use for energy. Glucose. Every single cell in your body uses that molecule for energy. Where do you get that glucose from? From food. When you eat food, the food is changed by your body into glucose, and then your cells use it for energy.
What about 5-hour energy? They don't use sugar.
they use drugs.
Basically, they give you chemicals that cause your liver, which stores sugar, to release its sugar, so you'll have energy.
Is that bad for you?
Not bad.
No,
That's good for you.
probably too much of it would be bad. Wait, she had her hand. Yes.
But on so many advertisements, it's like, this doesn't have glucose, so that's supposed to make it better for you.
Well, too much sugar, if your body gets too much sugar, you'll store it as fat. And the fat can build up, and too much fat can be bad for you. So, that's probably what they're talking about there. I don't know the commercial that you're talking about, but that might be what they're saying. Don't get too much of it. Yes?
Isn't glucose like what diabetics have to?
That's correct. Yeah, because they're low in blood sugar, you have to inject that. Yes.
Okay, so if you get the fatty sugar in you, and then you drink some 5-hour energy, does it make that go away?
What's that?
You drink some 5-hour energy, does it make the fatty sugar go away?
It'll make your liver, which stores sugar, release it into your bloodstream. Now, if you're low on liver sugar, then could potentially convert fat to sugar. It's a complicated process. We'll learn about it when we do the digestive system. But anyway, so this is a chemical reaction. Glucose is reacting with oxygen that you breathe. This is food that you eat and oxygen that you breathe. And that forms carbon dioxide and water. Carbon dioxide you breathe out. Did you know that?
Yes.
Every breath you breathe out, you get rid of carbon dioxide. And water stays in your body. So this is a common chemical reaction that goes on in your body. Food that you eat, glucose, combines with oxygen that you breathe. You form carbon dioxide and water. Those are kind of waste products. And that is going on in every cell in your body at every moment. So that's a chemical reaction that's important. We talk more about it next chapter. Now, if we're going to balance this equation, we have to put some numbers in front of the molecules. Let's just look at this figure right here, 6H2O. What does that mean?
6.
That means 6 separate H2O molecules. When it says 6H2O, here's what that means. 2,
Hey, Mr. Let's need some light on that
3,
board. You can't really see it.
4, 5,
Illustrated with your words.
6.
Can't you also write it like?
It actually appears on the TV a little bit brighter than it does in the scope. So I think they can see it. So when it says 6H2O, it means 1, 2, 3, 4, 5, 6 different H2O molecules. So what this equation is telling you is one of those combines with 6 oxygens to form 6 CO2s and 6 H2Os.
That's awesome.
You see? In actuality, it would be one of these, 6 of these, forms, the arrow means changes into, or yields. Did you learn this in physical science?
No.
That, and 6 of those, yields 6 CO2s and 6 H2Os. That's what that equation is saying.
5.
6 CO2s.
I know, but you wrote
Oh, I only drew 5? Oh.
Does it really matter?
So, this and that forms that and that. And you can see that it's the same amount of stuff over here as over here. For instance, C6. That means there are 6 carbons in this molecule. Are there 6 carbons on this side of the arrow? 1, 2, 3, 4, 5, 6. Yes, there are 6 carbons on this side of the arrow and 6 carbons on that side of the arrow. We say the equation is balanced. Nothing in a chemical reaction ever just disappears or appears from out of nowhere. The stuff on the left has to be the same amount as the stuff on the right. That's called a balanced chemical equation. And so if you count the number of carbons over here, it's the same as the number of carbons over here. The number of oxygens over here will be the same as the number of oxygens over here if you counted them all up. And so everything's nice and balanced. You should have learned how to do those balanced equations last year.
Yeah, not really.
We won't do many of them in this class, so that's lucky for you. But you have to be able to read these chemical equations that they give you and understand that if they're balanced.
I don't know.
Now, this is a diagram of a chemical reaction. This is showing you how the energy of the chemicals change through the reaction. Have you ever seen a diagram like this before?
No.
On the left side of the arrows, we call these things over here the reactants. The reactants are always what you start with in a chemical reaction. See that word, reactants?
Yep.
On the right side are what you end with. Those are called what? Products. So you start with reactants, you end with products. Now in this case, the energy went down. If you follow if you look, the reactants' energy is higher than the products' energy. You see energy on the left of the graph here. The higher you go up, the more energy it has.
Yep.
So we call this type of reaction an exothermic reaction. It gave off energy. If you start with high energy and you end with low energy, the energy must have gone somewhere. This is a reaction that might blow up, for instance. A reaction that might give off heat. Have you ever seen a chemical reaction like that? I'll give you an example of one. You light this paper on fire, it'll burn. That's a reaction that's like this. The paper has more energy in it than what's left after the burning, the ashes and smoke. What happened to the energy? It was given off in the reaction. So you can go from high energy to low energy in a reaction. Now, it takes some activation energy to get the reaction going. Activation energy is energy you put into it to get it started, like the light. If you light this paper with a lighter, that's the activation energy. That's the little bit of energy you got to give to get the reaction going. To get these things to go together to form their products, you got to give some energy to begin with. We call that activation. Now here is a different reaction. Do you see the reactants are low in energy and the products are high in energy? Yes.
Wonderful.
The endothermic?
Y'all, just as kind of a note, if you have to get up during class, you usually raise your hand and ask. So, and if you have to throw something away or something, just wait till the end.
How's it feel?
No big deal. You don't have to throw it away right away.
Worst cameraman ever.
Okay, so in this one, check this out. We start with low energy. We end with high energy. We have basically had to supply a lot of energy to get this reaction going. It's the kind of, did you ever do any chemical reactions in the lab last year that felt cold? Where the beaker felt cold when the reaction was happening? Didn't do anything like that?
She was a bad teacher.
Yeah, we did.
Sometimes you have to keep supplying energy, and energy can be taken from the air outside to get a reaction going.
Yeah, we did.
Some chemical reactions require energy. And so look how much activation energy you have to put in to get these reactants to do that. That's called an endothermic reaction. There's endothermic reactions and exothermic reactions. Now, a lot of the ones we'll be dealing with in biology are the kind that give off energy. Exothermic reaction is a typical one. And there is something that's called an enzyme that we will study. An enzyme is something, a chemical, a protein. Usually it's a protein, a type of molecule that lowers the activation energy. That makes it easier for two things to react. It's called an enzyme. I'm going to show you an example of of how an enzyme works. Here's an enzyme. It looks like a puzzle piece.
The substrate.
The substrates are the reactants. They're the things at the beginning of the reaction that come together and form something new. In this case, the two substrates come together, fit into the enzyme like puzzle pieces. You see them fitting there.
Perfect.
And these new products are created. Can you tell that we have something different than what we started with?
Yeah, the orange one just took a dot off.
This little piece right here came off and went on to this one.
More of a beige color, actually.
Okay.
We don't want to mislead our viewers.
So that's a sample chemical reaction. And it could be something like here we go. Losing the markers. Water plus oxygen forms hydrogen peroxide. This isn't a good one. Plus OH. That's a simple reaction. We start with two things, they change around, and we end up with two different things. It's not a balanced equation, but don't worry about that. That's what this is showing. We start with two things, two substrates. The substrates are what we start with, water and oxygen. And we end up with two different things, hydrogen peroxide and OH minus. And it took an enzyme to make that happen. The enzyme is where the reaction happens. The reaction would be difficult without the enzyme. The enzyme kind of turns the pieces in the right way to make them combine. So, lots of chemical reactions take place with enzymes. Here's a little video.
Enzymes act on specific substrates, such as sucrose, a disaccharide made up of glucose and fructose bonded together.
Quiet, please.
Each substrate fits into an active site on the surface of the enzyme. When the substrate binds to the active site, the enzyme alters its shape slightly. The enzyme substrate complex puts stress on the substrate. The products are released. In the case of sucrose, these products are glucose and fructose. After the reaction, the enzyme released is in its original shape and can go on to carry out the same reaction again and again.
See how that works?
Magic.
Simple chemical
You might
reaction.
gotta play again.
This is a slide with a whole, every little thing here is a little video showing an enzyme working.
Check it out.
Let's take a look at a few of these. We won't watch them all.
We only need to
Because
see
he
a
said
few.
not.
It's just too many.
Did you name
We
it
don't
the
have
rules?
time.
Yeah, do you teach this class?
Oh, here we go.
I'm not buying each.
Watch it go.
Catalysts are substances that speed chemical reactions without being used up in those reactions. In cells, catalysts are usually large globular proteins known as enzymes.
Oh, that was lame.
That was lame.
Alright,
This next one better be really good.
Redemption.
oh, this is a good one.
Better win.
The big green thing is the enzyme.
The enzyme attracts the reacting molecules or substrates to its active site, then releases the end products. Its effect is astounding. Each enzyme can assemble hundreds of thousands of new molecules every second.
Does it make that sound too?
Yeah, if you
Yeah, it
listen
does.
real close.
Yeah, they stick mic.
There's one called peroxidase that is in cells that does 300,000 reactions per second.
Yeah, I can do that sometimes.
1 second.
Like how it's like
300,000 molecules get put together.
Target can run a football field.
Fast.
It's like my 40.
Molecular motion is extremely fast. People don't really have a good grasp of how fast this stuff occurs. Okay, watch this enzyme work here.
Substrate molecules bind the active site of an enzyme molecule.
Let's get
This is an awful one.
yeah, this one's.
Takes
Hold your
forever.
comments.
After the
I'm sorry.
enzyme substrate complex has formed, catalysis can occur, followed by the release of the product or products of the reaction.
What? Jeez.
Now, they did show a couple things there that you do need to know about enzymes.
This guy's friend.
This area of the enzyme where the substrates attach, it's called the active site. The active site of the enzyme are where the substrates come in. So again, you start with substrates, you end with products.
Actually, it wasn't so bad.
Yeah. Guess what
Let's see what this one is.
so cool. This one looks good.
This one's not good. That's not
Enzymes are large proteins with complex three-dimensional shapes. Stabilized.
We're not going to watch that one. What about
Are there any Simpsons enzyme
this
clips?
one? I don't have any funny enzymes.
We
Oh, this
should
one's
make
cool.
one.
This is a good one.
Sure, if you want to.
Enzymes enable molecules called substrates to undergo a chemical change to form new substances called products. Each enzyme acts on a specific molecule or set of molecules called substrates. Each substrate fits into an area of the enzyme called the active site, This fitting together is often compared to a lock and key mechanism. However, the enzyme changes shape a little to fit with the substrate. In the enzyme-substrate complex, the enzyme holds the substrate or substrates in a position where a reaction can occur easily. After reaction, the enzyme releases the products and can go on to carry out the same reaction again and again.
See, wasn't that great? Substrates come in, two different substrates come in and combine and then leave. And the enzyme there can do another reaction then.
That's cool.
And so your body has these enzymes. Where are they? They're located in your cells. And the enzymes are used to either put things together or take things apart. For instance, you have an enzyme in your stomach that breaks apart proteins so that when you eat, your food will get digested. Your food will get broken down. The food doesn't, in your stomach, the food changes the way it looks because it's broken down chemically. A chemical reaction, and these enzymes are released by the cells in your stomach to tear up the food every time you eat. So, enzymes are very important for making chemical reactions occur in your body. Want to do one more? Yeah. That one's not good. That one's okay. Not good. Let's try this one.
An example of how enzymes function in the body is from the enzyme sucrase.
Watch it.
Sucrase resides on the surface of the microvilli on the intestinal epithelial mucosal cell surfaces.
This is in your intestines.
This animation presents a graphical representation of the way that sucrase catalyzes the hydrolysis of the common disaccharide sucrose, which we know as table sugar, into its component monosaccharides, glucose or blood sugar, and fructose or fruit sugar.
What?
Those were the biggest.
Hydrolysis is accomplished because when the sucrose molecule binds to the active site of the enzyme's configuration is changed so that the oxygen bridge between the two monosaccharides is exposed to water molecules in the solvent.
The sucrose and water
permits a water molecule to actually break the bond, the oxygen bridge, and attach the components of water, an OH to one of the monosaccharides and an H to the oxygen, which is still attached to the second monosaccharide. This effectively cleaves the bond between the two monosaccharides and converts the disaccharide into two separate sugars. Once this is accomplished, the enzyme's configuration is changed back to the original shape. The two monosaccharides float away, and the site becomes available for another sucrose molecule to bind, change the enzyme's configuration, and be hydrolyzed. This action can be repeated many times until the enzyme becomes denatured, is inhibited, or just wears out.
Okay, that was very complex language, but let me explain it in easy terms that you can understand. This is a simple chemical reaction here. It's sucrose plus water. And here we have the sucrose plus water. That's a little water molecule. See how big sucrose is. Sucrose is a big molecule. You know what sucrose is commonly called?
Table sugar.
Table sugar.
Ben. Table sugar.
It's like very nice, Bennett.
Fruit sugar.
Sorry.
How's it
So,
feel?
Fructose.
anytime if you take a spoonful of sugar, just a spoonful of sugar
Helps the medicine go down.
See? Sugar combines in your intestine with water.
Is that my largest?
Chemically, there are enzymes that change it to glucose and fructose. So let's watch this happen. This is actually, if you eat sugar, which you do every day, the sugar will combine with water. There's an enzyme in your intestines that changes it. Watch it combine. There we go. To glucose and fructose.
Magic.
Did you see how it changed?
Yeah.
Let's do it one more time so you can see. Here we go. Water and sugar combine.
Whoa.
There we go. They were changed. So this is a chemical reaction. We started with sucrose and water. We end it with glucose and fructose. We call sucrose and water the what?
The word.
There's a word describing this side.
Oh, reactants.
Reactants, or there's another word that we studied, substrates. So these are the reactants or substrates. Those words mean basically the same thing.
I heard that here.
Substrates or reactants. And what do we get at the end?
Product.
These are the products.
Oh!
Game.
Woo!
Look at that. Happiness in the classroom. How's it feel,
Y'all have
boys?
some game, don't you?
Yeah, we do.
We got more games.
Typical games.
I got more game than
It's like
random moments.
Give
Give me some of that.
Yeah, high five. High five.
Okay.
I know what you watching.
So that's 6.2. That's what you have to read tonight.
Yes.
How about, do you want one more time to sing the song?
Yes.
I'm gonna sing it.
Yes, song, yes.
You don't even need the music.
Here we go.
Hey, Tucker, it's all you. Tucker, it's all you.
I don't know.
Sing along.
There's antimony, arsenic, aluminum, selenium, and hydrogen, nitrogen, and rhenium, and
I grabbed it. What?
iron, ruthenium, uranium, europium, zirconium, lutetium, vanadium, lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. Tritium, and terbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and spermium, and silicon, and silver, and samarium, and bismuth, and beryllium, and barium. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercury, molybdenum and magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium, and calcium and chromium and curium. There's sulfur, californium and fermium, berkelium, and also mendelevium, titanium, and helium, and argon, kryptonium, radium, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones that
Listen to music, come to Harvard.
and then maybe many
Others
others.
would haven't been discovered.
No mas.
I couldn't get
No mas.
Dos mas.
Okay, will you turn around for me?
No mas. Okay.
Say goodbye, class.
Bye!
Bye, class.
Bye.
I don't know.